welcome to Software Craftsmanship McHenry County. A few announcements before we get started. First, thanks to our sponsors, Follett, for letting us use this space and this nice facility. And the Sal Group sponsors our meetup.com membership fees. And I'm sponsoring pizza this week. So I just want to let everyone know about the upcoming meetings. So in June, we're going to have a talk on community fiber from David Kutowski. And then in July, we're going to have a talk on web accessibility with Jason Zisman. And then I just want to say that I'm really excited about this month and upcoming talks because they all have a community focus, either a local focus or just everyone in general. So that's part of the reason that this group is created, to not only educate ourselves, but to give back. So with that, I'd like to hand it over to Brian.
Thank you. Tony, would you mind taking number 3 there, or 2 or 3? Thanks for having me. And Nathan, my son back there, he'll be presenting. Rand's son is also in our club, but is homesick. Rand has some involvement in our club from his son, and he asked me to present, and I found this to be a good match for what I understand that you guys have done. The robotics program through 4-H has been a very interesting endeavor. This is now, I'm completing my 5th year with the group. And it's been very interesting. When I started helping, I worked in tech support here at Follett. And there was a lot of my tech support troubleshooting background that came into helping the kids with the robots and with their code and so on. And now I've transitioned and I'm a business analyst here at Follett, helping take the project management's idea of what we want to add into the software and translating it into the developers' speak of what to code. And that has also been very useful in our club. So when we think about 4-H, is there anybody in the room that doesn't even know what 4-H is? All right, so we've all heard of it at least. Whenever I'm out and about and talking to people and I say 4-H, the first thing that comes to mind is somebody showing a cow at the county fair, or their sheep, or me when I was a kid, it was my rabbits. 4-H is definitely becoming more and more than just animals. 4-H's model is a learn by doing sort of model. Kids can sign up for any set of projects. There's a catalog of books. You sign up for a project and you get a project book. The idea is you go through that book over the course of the school year, or lots of families sign up. Nothing ever happens until school's out, and then it's a mad dash between May and June and July and to the county fair here in McHenry, end of July, first week of August. 4-H in and of itself is a global organization. There's over 7 million kids in the group. Then there's the national level, the state level, and the county level. We have over 500 kids here in McHenry County that are in 4-H. There's kind of 2 models. There's a community-based club where you meet every month, and there's a secretary and a treasurer and a president and a vice president, and you do service projects and you do a fundraiser, and you're all the time kind of learning Robert's Rules of Order and so on like that. Those community-based clubs, there is no specific focus. And then we have what we call spin clubs, or special interest clubs. There's a horse club, there's a dog club, there's rabbits, there's all different kinds of things, sewing, woodworking, all of the things. And then we have our robotics club. As I said, most of the time, this goes from the school year. We start in September and we run through April, end of April, for our club. 4-H does a conference judging sort of model. We have one of our robotics conference judges in the room. Dave Schwalis has been kind enough to help me out. I'm also the superintendent over the robotics area. He and another guy that I know from church have helped him come. Conference judging is very much just a kind of laid-back conversation. Let's talk about what you learned through the book. What was a struggle? What was the best thing you learned? It's trying to gauge mastery. There's the different blue ribbon, red ribbon, white ribbon. Blue ribbon is you learned something, you've mastered this level of woodworking, this level of sewing, this level of robotics. White or red, yeah, you did pretty good. You've got a little room to grow. White, yeah, yeah, that's not really even close. Kind of the idea. At the county fair, then kids can earn the option to the benefit of going to the state fair, which where they can go and show and basically do this, have the same conference judging over again, and have the option of going. That's not required. We can send a certain number of kids per section. Recently, 4-H is trying to reach much more out of the rural aspect and get into the more urban, get into the into kids that have no agriculture experience, no, they just have their backyard. Maybe they don't even have that. And so they've been working on getting into the different STEM opportunities for science and technology. So there's aerospace, they can build rockets, they can launch those. Bicycle, not exactly sure how that's exactly STEM in our true thinking, but clothing and textiles, and then we get into our computer science areas. And so we have programming, a number of different classes that they can enroll in when it comes to fair time. There's web design, we have electricity, geospatial, all the robotics areas. Some that is more junk drawer robotics is more about building simple machines and trying to get them to do some things, not so much the robot that we see here that you'll see on the screen. Small engines, new this year, they've got unmanned aerial vehicles, drones. So there's all different kinds of access that they're looking to get to, bringing more of the science, the technology into 4-H. Tractor. Yes, tractor as well, and welding. So our club, just to give you a brief overview about our club, how we work it and how we tie that into technology and things. Our club, we try and make it all about having fun while learning, developing friendships. Very much a social aspect of 4-H is building relationships, getting to know each other, building friendships. We learn the principles and practical applications of robotics and computer science. So this is where we start bringing in a lot of the next few slides where we talk about engineering design and so on. Then there's the hands-on basics of Lego Mindstorms. And so when they get to the end of the session, they should be able to take this robot, go to the computer, put in some blocks of code and make it do something. They could drive over and shoot you with it. And then at the end of our session, there is a competition. And I'll get into the details of that, but that is kind of the end goal that we work toward. This is what the students are working toward for the whole year. So this is the sets that we use, about $350 at Walmart. So if this looks like really something you would like to get your kids involved in or would like to have an excuse to have one in your own home, this is what we use. There's also the education model This is not available for public sale, but it's got a small motor, a couple large motors, the brain of the operations of this brick, different sensors, infrared, touch sensors, a gyro, and then all the different parts for putting something together. And we'll look through that a little bit later. So how we operate our club is going to go on 2 separate semesters. First semester, September through Christmas time. We have 8 meetings, and this is where we really try and instill in the kids, here is the engineering design model at work. Here is identifying the problem. What do we need the robot to do? Let's generate some possible ideas. Let's have a scrum. Let's have a brainstorming session about what do we need to do. This is where we bring in form versus function. We need this robot to be able to drive up and over the peak of a mountain. Well, do we want to have a robot on tracks, or do we want to have a robot on wheels? How are we going to deal with clearance? How are we going to deal with tipping, stability, all these different aspects? Brainstorming these ideas, deciding as a group. This is where teamwork comes in a lot, where we have to work on making sure we don't have one kid who's dominating the team and working together that way. Evaluate the design. Let's start building something. Let's see, does it work? Does it, okay, the design works. Is the code doing what we need it to do? Let's refine, let's refine, let's refine. And then, do we have a final product that works? Can we make it better? Repeat the process again and again and again. We talk about project planning. This is especially important when we get to second semester, as we'll mention in a moment. We talk about iterative design. They have to build a couple of different things and really getting them to come to a decision point that we have reached code frost, freeze on this particular task, we're not going to touch it again, and keep building upon and building upon and building upon. We talk about flowcharts, we talk about documentation, especially important, as we all know from writing code, documenting our code, so that when somebody else comes along later, they know what we were getting at here. That's a difficult step for the kids. Oftentimes they'll come back, we meet every other Tuesday, and 2 weeks later when they come back and they'll look at it and like, what were we doing here? And so documentation is important. So in each session, the engineering principles, I talk for a few minutes, try to keep it like 15 to 20 minutes. We meet for 2.5 hours. And then we go to kind of the hands-on coding basics of now, how do we get the robot to do what we want it to do? And so this is where I have one of our graduates, essentially. We have teens as teachers as a model in 4-H, where as you grow and as you learn and as you've mastered things, then you start teaching others about it. And so as our group is geared toward middle schoolers, and so as kids age out and are working into high school and are really kind of moved beyond some of these things, this is where they can come in and still be a part of the group and do the teaching. And so I'm going to have Nathan come up and kind of give you a crash course in 10 minutes or so of what the software can do and how we make those robots work.
Okay. So I'm Nathan. We've just wrapped up my 5th season with the club, which will be my 2nd as a leader coach. About 5 years ago, I was at the library and I saw a book about the Lego Mindstorms stuff, and being something of a computer geek way back then, or less than I am now, but I was, it looks interesting, I'll check it out. And After reading that, I'd been building Legos for a pretty long time, and Legos plus these robotic components looked like a lot of fun. And then we found out about the club through a friend of mine in the community club we were in at the time. And then we eventually wound up taking over the leadership of it when the previous leaders moved out of the state. So the software is drag and drop. There are different blocks that do different things, which for people who are used to text programming, it's gonna feel really clunky. When I first learned to use this, it was like, oh, this is easy. And then I spent summer learning Python. And then when I came back, it was awful. Like, it's so inefficient, but it's still really powerful. You can do a lot of stuff with it. And it teaches you to think in the way that you need to think in order to write text code effectively, which I think helped a lot when I did decide to spend the time learning Python, and it probably would have been a lot harder without experience from this. So this white area is your canvas. It's where you write your code, and every new program you add will start with one of these. This is where it all begins when you hit start on the robot. It'll start here and it runs left to right. And the blocks come from down here. And there are 6 tabs, and each color has a different purpose. So the green ones are the action blocks. They do things that you see. So these first 4 control motors, and then you can put things on the screen or play a sound. There's a light around the buttons on the front of the thing that you can change the color of. And this is basically where it all begins for the new members. I usually go over this the first time that we meet, and there are different parameters that you can change and different modes that change the way the block behaves. So the orange tab is your flow control, so looping, switch, also wait, and if you accidentally delete the start block, you can get another one from there.
Can you zoom in? Make it bigger.
Yeah. So that's a little better. So the one downside to this software is that your code is very horizontal, so you can't scroll easily, which is a little annoying. So the yellow, they're sensor blocks. You can use them to get data from one of your sensors. So this is the block for the infrared sensor. It can do a couple different things. Usually it's proximity. It works just like sonar but with light, and can tell you how far away you are from bumping into a wall or something. It also can connect to this little infrared remote. So you have a couple buttons that you can program, and not only can the sensor take input from pressing these buttons, but it also can tell you how far away it is and what direction it is. So you can mount the remote on one robot, and you can have another robot follow by tracking the beacon, which I've done exactly once, and it took some doing to keep them from colliding, but it wasn't that bad. So the way moving data, whereas in text code expression you can just call a function and put your parameters and all that in there. Instead, what you do is, if we want the heading, the angle to the infrared beacon, and use that for the motor power, you can draw this wire from one thing to another, and when it gets to this block, it'll pull all that data from the sensor, and this block doesn't actually take any real amount of time to execute, and then it'll get to this, and it won't move on from the motor block until it's finished moving the motor. After that, it'll stop. But that's just the way the flow of the program works. The red ones are for working with data, so you have variables and constant that you can use much in the same way, where you can assign a value to a variable and later use another variable block in read mode to reference that variable and use it for something. And there's array operations. You can work with kind of large amounts of data. It'll get kind of laggy because it's not a very powerful thing if you try to put too much in there, but it works. There's another block that does logic expressions. So these ones with a rounded plug in the yellow wire, those are numeric values, but the ones with the triangle and the green wire are Boolean value, true or false. And then there's math, round, compare, all kinds of stuff, and there's a random number block, which some of the kids at the club like to use when they get sidetracked and just making random sounds while the program is running. And then the advanced tab, we don't use a whole lot in club, but it does unlock a lot of stuff that you can do pretty easily in other more text code and building robots with like components that you've not so much ready-made and here are Legos, build something, than this is. There's file access. You can store data on the flash memory inside the brick, and then when it's plugged into your computer, you can upload that file to your laptop and view it. So it's useful mostly for when, if you have a program that's not behaving as it should, you can have it every second or two record the data from a sensor, and then you can look at that and see what's going on. You can also do Bluetooth communication between two of these units. We usually, the competition, the event, it happens on a 4x8 sheet of plywood with 2x4s around the edge, and you can bring, if the event you want to do requires a ramp, you build a ramp and you can put it on the table and stuff. But because of the scoring rule, you can, only one robot can be scoring points at the same at a time. So the judge can look at one and then the other robot. So usually the extent that we use this to is just sending, I'm done, you can go ahead now, to the other robot. But you can send any value that you can put into these wires, you can send across via Bluetooth. As a club and in my own fiddling with this at home, we haven't really explored that much, but it's definitely there. You can read like raw binary value from a sensor. I have no idea why you would want to do this. I've never used it. I guess if you're like developing aftermarket parts, you can do that. And then this last tab, when you open up a new project, it's empty. And this is because you can create, by selecting a section of code, you can create what Lego calls a my block, but it's just a function definition. So you can give it a name, and you can add inputs and outputs to it, and set that up however you like. And you can, if you have configure the block to have an input, there will be this output that pops up over here as it like comes into the code, which is pretty convenient. And then in this teal tab, it'll now pop up there and you can use it anywhere you like. So you can nest them inside each other, and you can do a lot of stuff with them, and it makes things a lot easier, especially when manipulating large sections of code when you have to be able to see it all. It makes things a whole lot easier, especially with this environment. So that's about the first semester of what I teach people condensed into a couple minutes. So I have a robot, which I'll be showing later, that does a lot more complicated stuff, and you can see some real world examples. And I'll skim over the code for that, but if you're interested afterwards, you can talk to me over there and I can show you all the details that you want. So,
Thank you. Good job.
no problem.
All right, so then after we've had 15, 20 minutes of teaching on what the blocks do, then I give them a hands-on task to do for that evening. And this takes the little bit of engineering talking, a little bit of the now hands-on about what they just learned, and we put that into practice. Sometimes it's simple in these very beginning days. We'll just set a chair on the floor and say, okay, program the robot to get around the chair, whether it's a square or a circle. Now, however you designed it, to go by degrees of rotation, by time, change it up, do something different. And then we just build upon that as we get through these 8 sessions as things get more complicated. The fun thing with this, we can take any noun and stick bot behind it, and it becomes part of our theme. The cow bot, there was this cardboard cow that was in some of the old curriculum, and we built tasks around it of first, drive around the cow, you need to circle it, and now we built in the medium motor and we built an arm for it. So now the cow is stuck in the mud, you need to go lift it out and pull it back and be able to go pick it up and successfully set it down. And now we're going to put the infrared sensor on it and the beacon on it, and now you need to be able to find the cow and go get it. And now we're going to put the cow on the other robot, and you need to be able to chase the cow and things. And so each night out of our 2.5 hours, about 1:45 or so, is the kids hands-on with the robots, learning, playing, not goofing around, but having fun doing it. So that's our first semester. That's the September through December's time frame. And then comes the challenge. And this is really where the meat of what did I learn and how well do I really know what I'm doing comes into play. We have 16 members in our club max. We then divide those into 2 teams of 8, 2 robots per table. As Nate described, it's a 4x8 sheet of plywood with 2x4s around the outside to keep the robots from falling off. And the state 4-H robotics team comes up with, generally it's about 15 different tasks that you can do. You've got a 3-minute max for your robots to complete whatever. And so this becomes also part of the challenge for them, is the decision-making process of, as the 8 of us, 4 people per robot, what are we going to do? What's the most points we can score? Because, well, that's fun. But how are we going to lay it out on the table what order are we going to have the robots do, which tasks are our robot going to do and your robot's going to do. During the competition, they get 3 different table runs. They get 3 attempts to score their points. This is an example from this year. The theme was STEM bots. A little hard to read. It was all about different science, technology things, and this particular task was chemical mixing. Mixing chemicals is an important, with the different qualities to become a good chemist. Mix 4 different chemicals by pouring them one at a time into a beaker. Bonus points if it'll be awarded if it's done by 2 robots, pouring 2 chemicals each. Trying to add some extra complexity to having not just one do it, but the 2 of them work together. And then different scoring methods and also the fine details of each chemical must be poured in the beaker one at a time. You can't just dump them all 4 in at once. The beaker must be 3D, as you'll see in the video later. A lot of the things are represented just kind of 2-dimensional on the mat that we play on. And it's about getting something from here to there, but there's an added level of complexity if you have to actually pick something up and set it down, and so on. And so they have these different things to choose from. What are the points? How would we do it? What kind of robot would we need? What's the basics of this task? I need to get something from somewhere to somewhere else, and moving forward from there. And so this is where a lot of the project planning comes into place, because we generally say, all right, in 3 minutes, each robot can probably do 3 tasks, and then you have to coordinate. And so within these 8 meetings that we have between now and we get the challenge, and the first thing we do is basically have a meeting where we just sit and talk about what do we need to do here? What are our requirements? What are our constraints? What kind of robot do we need? Engineering design model coming into play. How can we accomplish this? Can we accomplish it all? No. We have to avoid scope creep. We have to maintain our boundaries. This is where a lot of my job comes into play now, of like, nope. Setting a project plan, iterative build. You've got task 1 done, don't touch it again, unless it breaks. These robots are expensive, but they're not $1,000 machines either. You can program it to do exactly what it's supposed to do, and the motors might be just a little off, and it starts going this direction instead of going straight and things. And so there's always little tweaks here and there that they do. And so this is the kind of putting into practice and then really working toward it. And then when we get to the actual competition day, there's different awards, teamwork, robot design, programming award, best table score. There's some other awards that are very subjective and we don't really understand how they get awarded, but it's a little bit of a participation thing of team spirit award and some things like that. But this is that whole second semester, and they work on it, and each night they improve, hopefully. That's the goal, of course. There are some times where we have to schedule some emergency practices at the end. But this is then kind of what we are working toward. Challenges generally mid to late April. We are blessed to be able to have a competition here in Lake and McHenry counties. There are some that are other regional ones around the Chicagoland area, and then everybody else meets downstate in Springfield. So we don't have to drive 3 hours to go to our competition. It's wonderful. Again, most of the schools, most of the clubs we're competing with are middle schools, where 4-H is partnering with the school to have an after-school club that is Lego Robotics. And so our club is one of the few that is not a school-based club. There's a couple at the library and things like that. And this is, again, is their day to shine. This is what is hopefully fun, as Nathan can tell you. You can have something that was working perfectly fine Thursday night at the last practice, and you get there Saturday morning and it does nothing.
I have so many great stories.
Nothing right, or does everything wrong.
How much fun we had.
We have had experiences where, the lighting makes a big difference, especially when they're using the light sensor to do a line follower. And what worked perfectly well in our practice room is now in a gymnasium with big giant halogen lights. And it can't tell the difference between white and black, let alone black and red and things. And or all of a sudden you're in this giant room with lots of other robots that are trying to Bluetooth connect, and all of a sudden there's you're talking to some robot on the other side of the gym. And it can be quite an experience. But this year went really well. All right, we'll stop there because the rest of it is just the award ceremony. Our club did really, really well. We're very proud to be able to bring home programming award by one of our teams. The Team Purple also brought home the design award and best table run. Grand champion, best table run. Yes, thank you. So you saw in there that you can be a little liberal with the definition of something. Computer build was defined as bringing computer parts from one area to a build desk. That was completed by rolling tape rolls from one area to another. The chemical mixing, they had different chemicals lined up on the side of the beaker and just kind of walked by and nudged them off into the beaker. So you can be a little bit flexible and gracious with things. I had the pleasure of being a judge this year, so I got to see a lot of different clubs and how they interpreted things. It was fun. Some had get the trash from one place to another, and they had it on a zip line made out of paperclip and fishing wire and a little straw that just drove out from under it, and it all slid down into the trash bin. So there's some level of engineering just in how they set up the table and what they build. And we like to say that the first time that we get the challenge, there is kind of this like, how can we kind of define this really easily? We had one where the dog, one year we were doing dog bots, and there was dog agility drills, and you had to drive over this thing. And one of the kids like, what if we made the robot really, really wide and it just drove over the top of it? Like, okay, so you have a future as a lawyer, but I don't think that really applies here. All we need to, so there's some guidance as to exactly how do we do that. Yep. All right, so then after our club year wraps up, students that have a robot at home have the option of then going on and doing something more at the county fair. There are, as we saw earlier in the project, then you can sign up for classes, you can do different things. There are different levels. One of the levels is just make the robot do something. One is make it follow a line follower. As you saw a number of the things that when the robot was kind of shuffling its way back and forth, that was following the color sensor, following the line to make sure it got to the right place. There are little mini challenges that they can do. There's open source robotics, and then there's innovations, which is kind of the catch-all bucket of other. Last year, Nathan made basically an automatic transmission sort of thing. Again, conference judging, we review the book, we review the code, and it's a discussion. For the county fair, our participation in the county fair is we bring the tables, we bring the robots, we do demonstrations, get the word out about the club. And we also help pick up trash around the fairgrounds as kind of our service project for the year. And then again, people can move on to the state fair with those exhibits. We're going to have Malcolm do a demonstration. Malcolm's robot is designed to basically use the infrared as a remote, and so you could drive back and forth, and I believe he even had the ball shooter working, is that right? So it's probably better for all of our safety that Malcolm's not here, but so fortunately that he's not. I was looking forward to it. It was Malcolm's first year in the club, and now at Christmas time, I think it was, he got a robot, and it is great to see the growth in the kids that do have robots. We had 3 different families that invested or had family members help invest in a robot for Christmas. And those kids that were maybe a little struggling at the beginning of the year, wow, their knowledge just took off when they could go home and play with it and work on it. And now Nathan's got something that I don't understand. So,
But it looks dangerous.
Okay. So this is a continuation of the project that I did for the individual fair project a couple years ago. You may remember the robot that had the motors mounted to that triangular wooden piece. Basically, it's using Kiwi Drive, which is a different drive platform that almost no one's heard of. But the interesting thing about this is that it can drive in any direction without having to rotate to face that direction first. So before I tell more about that, I'll give a quick demonstration. So there are 3 of these special wheels that are at 120-degree angles to each other, and they have these rollers that roll the other way, so the wheel only has traction on one direction. So that way you can have them not all be parallel and actually get somewhere. Especially when I'm driving side to side, it drifts a lot. Haven't figured out how to fix that yet, but that's just the way robotics is. So that's what it does. So when I first attempted this, I had not yet taken trigonometry, and there wasn't a good way to take the Cartesian coordinates that a joystick gives you and turn that into an angle that I need to go drive in this direction. But I started trig a couple months ago, and now I can do it again, and I can make it work. So these are the wheels that it uses. These gray, the black rollers are pretty loose, so it doesn't affect your speed at all, really. But they allow it to slide side to side. For projects like this, they're really fun to work with, but for larger robots that like the more big dog, huge robot competitions, use wheels like this. Can't carry as much weight as other wheels, but you usually would be able to make up for it in the maneuverability that you gain. So this is a view from the top. You can kind of see the 2 there. I've got my mouse. This thing here is a receiver for a perfectly ordinary PlayStation 2 remote, and there's a aftermarket part that the receiver plugs into, and then it can plug into the robot through a cable just the same as any other sensor or motor does. This thing in the middle is the brain of the whole thing. You can see the light here that I mentioned earlier. Basically, it is a very much scaled down Linux computer, which you can't really get to the Linux part of the computer from here, but there are other firmwares that you can get from third party that you can put on an SD card and plug into the port on the side, and then you can access the more developer-friendly aspects of Linux, so you can program in Python, which I've wanted to do for a long time. I haven't gotten around to working on it yet. So this is a summing up of the trigonometry I needed to learn to do to go from Cartesian coordinates into polar coordinates, which for this kind of robot are a whole lot more useful, where you have a point and then you have an angle and distance away from the angle, I can use the angle to tell the robot what way to go, and how far away kind of translates to speed. So using the pretty basic trigonometry that you learn in the first couple weeks, I was able to unlock the solution to one of the two big roadblocks I'd had with it earlier, which was very exciting. And then the other part was taking movement in a flat plane, which you would typically think of as a 2 dimensions, and trying to figure out how to split that motion between 3 wheels. So using my very professional looking graphic here, which I did in Microsoft Paint because I did not have time to pull anything else together, you can have the point 0, 0 that I've marked, and imagine that being the center of mass for the robot, and knowing only the angle A and then R, the radius, based on the point marked in red, the robot can use trigonometry to figure out what the X and Y values are given the polar coordinates, and it uses the Y to decide how fast the motor on that particular side works. And at a glance, you could just, why convert to polar coordinates at all if you can just have X and Y? But when you go, we have 3 wheels to work with, you have to do that math 3 times, and the angle is different for each one. And then computing how much each side has to contribute to the overall motion, you can figure out that stuff in not a whole lot of work. So the code for it is here. So this is basically the main loop of the thing, and I'm using 2 of the teal my blocks that are functions I've defined. So there are a lot of these numeric wires going around, which is a little messy, but so this is the first of the 2, and this does some post-processing on the polar coordinate number that I get after doing the trigonometry. So this is another one that I made that takes Cartesian coordinates in and polar coordinates out. And the way it works is the range of the tangent function, which is what you use, you only get like 0, negative 90 to positive 90, and I need a full 360 degrees of numbers in order to drive in any direction. If I just left it as is, I could drive forward and to the right, and that's it. So this does some math on that to fix the solution, and this was one of the other things I had issues with, where my original version was very, very laggy because I had to use nested if statements, which are not only a pain to program, but at least in this software, really ate up processing power, and it was just, there's a very noticeable delay between moving the joystick and anything actually happening. So I've been working mostly yesterday to try to get this up and running well for this event, and had to come up with some pretty creative solutions to deal with stuff. And then over here, it just sends those values out so the block can pass them on to the rest of the program. So the other block I've used, this takes the polar coordinates in and does the math to figure out what power each motor needs to be at. This is the block that basically I can get all the data from the remote, and it's, when you upgrade from this with 5 buttons to this with 16 buttons and 2 joysticks, you can do a lot. But for this project, I'm only using just the joysticks, but you can read all the buttons, and some of the buttons you can either have like variable pressure and read on like a % scale how much pressure you're applying to the button, which is pretty cool. So this section here is one of the cool things that the math block can do. You can put it into advanced mode, and then you can just type an expression in here just like you would with text code, and instead of having just being able to call a function that'll return a number, you have 4 inputs, A, B, C, and D, that you can send values into to work with. So that's another part that's a good introduction for someone who has one of these and wants to move on to text code and things like that. So then these 3 blocks just do the computation. So this is kind of the base that it runs to figure it out, and then these just have plus 120 to get the next wheel around, and plus 240 to get the next one around, and then it sends all those out to the rest of the program. And then this is the way switches work in the software. You have 2 cases that you can set. This one is the one that's run when the joystick is anywhere but in the center. Actually, no, I'm wrong. This is the one that runs when the joystick's anywhere but in the center. And these 3 values come right out of the Kiwi Motors block and go into these blocks, and those motor speeds are immediately set. And the way this block is set up is it's in the on mode, where it just starts that motor running and just leaves it running until it's instructed to do something else. So this is another one kind of like the yellow ones that don't take up any time. So it'll just start the motor running in the background, and it'll do whatever it was doing until it needs to do something else. This is on an infinite loop, which just loops as fast as it can. So it, as close as possible to real-time updates, like maybe a 1/10 of a second worth of lag in there, which compared to a 1.5 seconds is pretty good. So then in the 0 case, this is what runs when the joystick is in the center. I originally, because of the way the math works, there was somewhere there was a divide by 0 and an error code would come out. So I had to say, well, if I can tell from other ways that the joystick is in the center, and if so, run this case that does something else. So all this one does is takes data from the x-axis of the left joystick to rotate in place. But that's all it can do when the other joystick is in the middle, because it's not actually going anywhere when that happens. So that's a quick overview of how the code works. I've set my laptop up with the TV back in the corner, so if you want to take a closer look at it and learn about how the software works, I would be really happy to show you.
Go ahead and demo it again.
Oh, again? Okay.
Do a small figure eight around the outlets.
Might be kind of hard. Yeah, the next thing I need to do is to get rid of the drift that happens. This is a gyroscope, and it can like zero out, and I can tell how many degrees I am off. So the next project is to use that to keep it straight and not get all off. Did I do the wrong thing? I did do the wrong thing. So you can see how the wheels change speeds, and it affects the way.
No, it's almost like it moves like a hovercraft.
Yeah, kind of. The original version, you could see the wheels a lot better, but in order for a mechanical problem that they were kind of just sagging in the middle because there wasn't support from the other side. So that was one of the things I fixed. The original version I had built on a sheet of wood that I cut into a triangle because Legos are rectangular and it's hard to use rectangular Legos to build a triangle. But I did spend a Sunday afternoon trying to build a triangle out of rectangles, and I succeeded. So no wooden part this time. But so that's what it does right now. There will be more stuff added in the future, but it's a work in progress. So that's all I've got.
All right, so that kind of wraps up what we planned to present today. So any questions that you have for me about the club, about 4-H, about robotics, anything detailed about this, you ask him. I can kind of make it go straight. There's a tank block one, and you just go like this.
So, do you make it? Are there openings for next year at the club?
There are. We have 16. We have a couple that graduated out. I ended up actually with 15. So I do have everybody in the club. When I kind of did my exit interview, gave them their blue ribbon for being in the challenge phase. Everybody said they wanted to come back, which is always a nice, good feeling. So I think we have 3, 4, 5 openings, something like that. Robotic Rovers at gmail.com. So if you've got an interested youngster in your life, get on that right away. I've been very blessed to never have to roll the dice and pick 3 out of 5 kids on a waiting list. So it's always just worked out. So that's been nice.
Is there an age limit?
I define it as my sweet spot is like 11 to 14. And this year I do have a 10-year-old in it that's got a robot, and he knows all he's doing. He was a good coach to other mentors. If we don't have 16 in that, then I'm more willing to go outside of the age range, let kids that are kind of aged out participate, and so that's how I do it. Where since I'm, the others are very limited by, well, who's enrolled in my middle school, that's my age. Some schools do it. This is just a club for 8th graders. They have their different ways of organizing, but so far it's worked out nicely. Yeah.
Does your team participate in first at all?
Right, so Dan's question about FIRST, meaning First Lego League, First Tech Challenge, First, what's FRC stand for?
First Robotics Challenge.
First Robotics Challenge, is a series of Lego sponsored sort of thing. No, we don't. It's a different level of things and a different, you need to know more. I don't see it necessarily as sort of an introductory level. Our focus is very narrow. I want to be able to take somebody that knows absolutely nothing and be able to kind of teach them, groom them through, and then after a year or two, if they really are excited, then they can go off and find a FLL or FTC group and be a part of. Plus, it's just, that's overwhelming for me. So this is my one little focus, and this is my box, and I'm staying in it.
Yeah, I mean, what you do is, it seems very similar to what FL does.
Mhm.
So it's,
The kids that I've had in the club that have also been in FLL have been originally excited by the challenge phase, because in FLL, all the teams do the same thing, if I remember this and understand this correctly. They all have this one goal, and it's very kind of constrained, and you all do the same thing. And when they get to this challenge phase, I'm like, here, choose what you want to do, and how you're going to lay it out on the playing surface, and what order you're going to do it in. It's like, oh, this is freedom. Oh, I got to make decisions. And it can work both ways for them.
Yeah, I have a question, but it's sort of about 4-H, not robotics. So there's other robotics questions. Get those out of the way first.
go ahead, Ralph.
See, because everybody's wondering, what's he going to ask?
Yeah, right.
No, actually, I heard earlier you were mentioning about different things that 4-H is getting into and STEM, and that there was some, besides the tractor, electricity and things like that. And I just wanted to put out there that there's a group of people in the McHenry County area that are very active in electronics and radio. And this last year, we'll be doing it again this year, is we've been a part of the STEM Day for the Boy Scouts. And they have like a radio merit badge, and they have robotics and things like this. And the group that we have was talking about electronics, electricity, and actually amateur radio, getting on here, what is that involved with that? So if there's a connection in there, maybe that we might want to talk to you about that, because we're looking to kind of expand and go on, besides the Boy Scouts, putting it up for a larger audience.
Mm-hmm. Very good. I can put you in touch with the leadership and see what we can do with it.
Are you going to take me to the leader?
Yes. Yes. And the county 4-H leadership is always looking for new spin clubs, new ways of getting kids involved. Again, it's all about learning by doing, and you can come up with a very loose curriculum or very in-depth curriculum. It's about getting the kids hands-on and doing stuff, whether it's soldering boards together or doing whatever in coding world, programming world. Just trying to get them more exposed and interested. Any other questions? I appreciate your time. I appreciate your kindness. As I had it written down, it was starting at 7, so sorry I was late. We're on time, but not prepared. So thank you very much. I appreciate it being
And
here.
I just wanted to add too, that was very creative problem solving and using mathematics to be able to solve that in 3-dimensional. So kudos.